All right, so today we're going to start by finishing up chapter 3, which is section 3.7. So it's looking at solving systems of equations graphically. Does anybody remember how you do that? Like if you want to graph a system and then you look at the graph, what are you looking for to find the answer? Remember, Jane?
An intersect.
Yeah, you're looking for an intersect. And depending on the kind of system you have, that could be one intersection point. If it's two lines that could intersect in one spot, they could be parallel. Okay, there's different cases that could happen. But we can also get into cases like a parabola and a line. So now you're talking about possibly the line could hit the parabola twice, could hit once, or not at all. Okay, so we'll look at some other systems other than just lines. Okay, so a system of equations is when you have to solve two or more equations for two or more variables. Generally, in Algebra 1, you stick to two equations, two variables. In Algebra 2, you might step up to three equations and three variables. Okay, when you start getting into three variables, we generally don't do the graphing approach as much. Anybody know why? How come two variables is pretty easy to graph, but then what happens when you do three variables? Yeah?
Well, their lines might not intersect at the same
They might not intersect at the same point, but that would still be equations with two variables if they're lines. What happens if you step up to three variables? Yeah?
It would be 3D.
Yeah, well, we start to get into planes. We start to get into two-dimensional drawings. Lines are really one-dimensional. So now we're trying to find where planes would intersect, and that can be harder to draw. So generally, with more than two variables, we stick to a more algebraic approach. But if we are going to stick with just two variables, generally you have to find an x and a y value because you're looking for a location. Okay? And that's an ordered pair. Okay? So the solution of a system with two variables is a coordinate. Okay? So just make sure you always write both the x and the y. And graphically, we just said that the solution is the point of intersection. Okay, there's other methods to solve systems with two variables or even three variables. Like you can do substitution. I know we've looked at that. You can do elimination. Has anyone ever done a matrix? Yeah, you can do a matrix. Matrices work very well, especially when you start to get into more and more variables. I really wouldn't want to do substitution with a problem with like 4 or 5 variables. A matrix would be a little easier. Okay, but today we're going to focus pretty much just on graphing. Okay, so let's see if we can solve that system graphically. Now, using the kind of calculators we have, what would you have to do first here if you want to solve that graphically? It's not ready. Yep.
You have to get everything equal to y.
Yeah, we've got to get y by itself. Okay, so in order to get y by itself, I would have to do two things. Can someone tell me the first thing I would have to do? Jane?
You would subtract the 2x.
Subtract the 2x, and the second thing?
Divide by 3.
Divide by 3. All right, so when I subtract the 2x, it's going to become negative 2x. I'm still going to have the plus 5. And now I'm going to divide everything through by 3. Okay, so there's my first equation. Second equation, we're going to do the same idea. We're going to add the 3x and divide by 5. So it's going to be 3/5 x plus 21/5. Okay, what's the 3/5 called again? And the negative 2/3, that's the
Constant.
Well, it's the coefficient of x. The constant would be the number at the end. The 3/5 and the negative 2/3 is the slope of the line. And then the constant, that's your y-intercept. All right, so there's a couple ways you can type that in. The x you can think of as really being in the top of the fraction. So if you want to avoid parentheses, what you could do is type it in as negative 2x divided by 3. And then plus, and I am going to put the 5/3 in parentheses because I don't want it to, I want it to do 5 divided by 3 and then add that whole result. You might be able to get away without parentheses. Let's just graph it and make sure that looks right. So it looks like, yeah, it should be heading down, and 5/3 is a y-intercept of 1.6, 1.7 roughly. And that looks good. Okay, I'll show you a different way you can type it in, and I'll do it on the second one. You could type in 3/5, but you would have to put it in parentheses, x. Okay, you can type it in just like that. If you don't put it in parentheses, it's going to do 3 divided by 5x, which is not what you'd want. So 3/5 x plus 21/5. Okay, hit graph. And clearly these are not parallel lines, the slopes are different. So they're going to intersect in exactly one spot. And can someone remind me the steps on the calculator to find intersection? Yeah? Second calc. And intersect. And you have to pick a point on your first curve, which is my blue one. Pick a point on the red one. And the guess doesn't matter because there's only one intersection. If there were multiple, you have to put the guess closer to the one you want. Okay, so the intersection point is negative 2, 3. Any questions on how we found the intersection point with the two lines? Okay, so sometimes it might already be arranged for y for you. If it's not, you need to do that first. Okay, let's try this one. It's a cubic and a parabola. How many times can a cubic and a parabola cross each other? At most. You want to have a guess? Abby?
5.
5? I don't think it can cross that many times.
3.
I think it can cross up to 3. Because if you think of your cubic like that, and maybe a parabola like that, I don't really think you can get any more crossings than that. I think that would be it. So you could have at most 3. You could definitely get 2. You could get 1. Could you get none? Sam?
No.
No, how come?
Because it's, whether the parabola is above or below, where it goes up and down, it's always going to go all the way up and down.
Yeah, the cubic is going to go up and down forever, so the parabola is going to hit it somewhere. Okay, so let's graph that and let's see what we got. Yes, we got negative x cubed plus 3x squared plus x minus 3. Okay, so that's that. And negative 2x squared plus 5. So the reason I asked you how many times it could cross is because we've got to keep in mind things could go off the screen. Okay, I can see all the turns the cubic is making, so nothing's off the screen here. Well, the turns aren't off the screen. So how many times does it look like the cubic and the parabola are going to cross? Yeah? 3. I think it is going to cross a third time. And if you set your y min lower, let's try like negative 40. I think you'll see that the cubic and the parabola are getting closer and closer. Okay, so there's my cubic. Here's the parabola. And now you can definitely see they're getting closer and closer. Whether or not I have the intersection point yet, I'm not sure. Probably if you set it to negative 50, I can guarantee you'll have it at that point. Okay, so I'll calculate the one that's at the bottom. If somebody else could calculate the two that are up near where it's turning, okay, and I'll get the third one. Okay, so this time, pick a point on the blue and the red. That doesn't matter where. But for my guess, I do have to put it closer to the intersect. Okay, so that one is about 4.87, negative 42.39. Alright, so there's a 4.87, negative 42.39. Okay, so that's one answer. Okay, does anybody have the other one of the other intersection points at the top? Yep, Jan.
The left one is
Left one, okay.
negative 1.22
2, yep.
and 2.03.
2.03. All right, thank you. And does anybody else have the third one? Yeah, Megan.
1.35 and 1.36.
1.35, 1.36. All right, so that's kind of a messy answers. To do that algebraically could be challenging, right? If you wanted to solve it with algebra, you'd have to hope that something special happened, like you could do factor by grouping or something like that. All right, any questions on that? Okay, so there's a cubic and a parabola crossing as many times as they possibly could. All right, the last one, let's do it algebraically first, and then we'll do it graphically. All right, so how would I do that algebraically? What would be a good approach? Yep.
You could plug in 3x for y in the first one.
Yeah, this one is set up to do substitution perfectly because it's already solved for y on both of them. So just plug in 3x equals x cubed minus x. And now to solve it, we want to get it equal to what? Oh, Sean?
X. Or
Well, I don't think we're going to be able to get x by itself, like an equation, like an algebra 1 kind of equation, just because there's x's with different exponents. So another approach would be to get it equal to, like if you're solving a quadratic, you do this. Yeah, we want to get it equal to 0, and then we're going to hope that we can factor it or something like that. So we get 0 equals x cubed, and what would be my x term? How about, yeah, Sam?
Minus 4.
Minus 4x. Right. And Trevor, do you see anything I can do there on the right-hand side? Not sure. Anyone help him out? What? Something we can do. A lot of times it's helpful because it'll make the exponents smaller. Yeah.
Can you factor?
You can factor that. How does that factor?
It would be x squared plus 2 and x minus 2.
Oh, I don't think you're going to be able to factor it with the two sets of parentheses
Oh.
yet. You will in a second.
So you can take out a net.
But you can do a simpler form of factoring, which is just to take out the greatest common factor. And what would that leave you with?
X squared minus 4.
X squared minus 4. Now you can do what you were thinking of. And what do you get when you factor x squared minus 4?
X minus 2x plus 2.
Yep. Hey, so based on that factoring very nicely, now we can write our three answers. Okay. What would be my three answers for x? Okay.
x equals
and x equals 0. Exactly. Now, are we done? What else do I still have to do? I only did half the problem. I mean, I did the hard half. The second half is going to be super quick. Yeah?
So for y.
Right, I didn't get any of my y values yet. So now I need to plug in 0, 2, and negative 2. Does it matter which equation I use? It shouldn't if I found the correct x's. So let's just use y equals 3x. So basically just triple all your x values. So we get 0, 6, negative 6. If you're going to write it like that, it's probably a good idea to write them in exactly the same order. So I know 0 goes with 0, 2 goes with 6, negative 2 goes with negative 6. If that's kind of confusing, then just write 3 separate coordinates. 0, 0, 2, 6, negative 2, negative 6. Okay, so just don't forget to get the y values as well. Okay, now let's do it graphically. Okay, even graphically, there's a couple ways you could do it. You could take what we had at this step, type that in, and look for roots, or just type in the original problem and look for intersects. Okay, I'm going to do the original problem. So we've got x cubed minus x and 3x. I should probably set my window back. Well, I guess you can kind of see it there, so that's okay. But if you want to see it even better, if you do zoom 6, it'll just zoom in right to the area we need to see. Okay, I'm not going to calculate all of them, but I mean you can definitely see 0, 0. Okay, and I'll calculate one of them just to practice that again. So do an intersect, blue, red, and I'll do the one up here. Okay, so we get the point 26, which was my second one. And if you did the third one, you'd get negative 2, negative 6. Okay, so any questions on how you do intersect to find the other ones? All right, so that's pretty much it for 3.7. Just keep in mind that things can go off the screen. So based on your highest exponent, whether it's even or odd, and based off the number in front, whether it's positive or negative, you should know how many twists and turns the graph is going to take. So if you're not seeing all the twists and turns, then be careful that something doesn't happen off the screen. Okay, let's take a look at 4.1. So chapter 3 was all about polynomial functions. Okay. Nice thing about polynomials is that the domain is always what? For every polynomial. Leo? All real numbers, yep. You can take any number you want and cube it and square it and subtract 5 and multiply by 3. You can do any of that. Now chapter 4 is going to be about rational functions. So rational, what does it mean if something is rational? It can be written how?
As a fraction.
As a fraction. So we're going to look at functions that have variables, and a lot of times the variables are going to be at the bottom of a fraction. Well, now when you have fractions, you have to be careful that you don't ever do what? What can't you do in a fraction?
Divide by 0.
Can't divide by 0. So now there might be restrictions on the domain. Okay. So basically, the simplest way to describe a rational function is it's a fraction where the top and the bottom are both polynomials. So it's a fraction where the top and the bottom are both polynomials. The only polynomial you are not allowed to put in the bottom in general is the 0 polynomial. You can't put 0 in the bottom. Right, so we got to keep that in mind if you had something like this. There's a restriction on values you can use for x there. Only one number you're not allowed to use for x. What would be the one number you can't use? Yeah. Go ahead, Matt. 2. And something weird is going to happen as you get close to 2 on each side of it. And by each side, I mean as you get close to like 1.99999, that's approaching 2 from the negative side, or as you approach 2 from the positive side, like 2.000001. Okay, so a lot of times we're going to explore the behavior on each side of 2, very, very close to it. Okay, like 1.99, 2.001. And that'll give us an idea of the graph. That's an example, nothing I'm going to do with it at the moment, but that's an example of a rational function. That's another example of a rational function. When we look at rational functions, something that's going to tell us a little bit about them is if you look at the exponent in the top, the biggest one, and you look at the biggest one in the bottom. We're going to kind of break it into cases based on that. Is the exponent in the top bigger? Is the exponent in the bottom bigger? Or are they the same? Okay, so throughout the week, we'll look at those different cases. Anytime the exponent in the bottom is bigger, there's a certain thing that will always happen. Okay? When the exponent in the top is bigger, that's usually going to involve doing some long division to figure out something. Okay? And we'll talk about that. Okay, so domain of rational functions. It's not really super complicated to explain. It's basically any number that doesn't make the denominator 0. It's the only thing you got to be careful about. Do not make the denominator 0. Okay, range, we'll talk more about that, but that's a little trickier. Okay, a lot of times we're going to use the calculator to help us with the range, because rational functions can look really different than anything you've seen before. So eventually you kind of get a feel for what they look like, but at first the calculator is helpful. Okay. So let's see if we can find the domain of some of these functions. Okay, what's the domain here? How about, and I'd like you to word it and tell me what it is. Tell me, well, you know what, you can word it either way. We're going to do both. You're going to tell me what it is and then tell me what it isn't. There's different ways you can write it. Anybody think they can give me one way to describe the domain here? Sam?
All real numbers except 3.
All right, so she's telling me what it isn't. She's saying it's everything except 3. Okay, so all reals except 3. How could I write that in interval notation? I could pick any number from what to what, and then you're also going to have to do another interval. Remember how we write that, Leo?
Negative v to 3, and 3 positive v not including 3.
Right, not including anything. So you can pick from negative 3 to 3, or you can pick from 3 to infinity. So here I'm describing what it is. Up at the top, we're saying basically what it isn't. It's everything except 3. Okay, so different ways you can write it. I would just be familiar with both. Okay, let's try this one. B. This one you really can't just look at it and get the answer. So, Dylan, what do I have to be careful about? We have to make sure that the denominator is not what?
Equal to 0.
Equal to 0. So let's set the denominator equal to 0 and find out the values we can't use. Okay, so we've got 0 equals x squared plus x minus 2. And I think that'll factor. Anybody tell me how that would factor? Yep.
X plus 2, X minus 1.
Yep, x plus 2, x minus 1. And now that he's factored it, it makes it much easier to figure out the two numbers that would make the denominator 0. So Tanya, what would be the two values that would make the denominator 0?
Negative 2 and 1.
Negative 2 and 1. So I'm just going to write all reals except negative 2 and 1. If I wanted to do it as an interval, I would need 3. From negative infinity to negative 2, from negative 2 to 1, from 1 to infinity, parentheses on everything. Questions on that? Right, and this one. Actually, this one's a little bit easier than B because the factoring is already done for you. So Tessa, what would be the values I am not allowed to use in the denominator here? Yeah, so all reals except 2 and negative 4. So 2 and negative 4 on the graph are going to be things you want to investigate. What's happening near those numbers? Okay. What's happening at negative 4.001? Where's your y value? What's happening at negative 3.99? Okay, where's your y value there? Any questions on that? All right. So the simplest rational function you can have is basically just the reciprocal function, 1 over x. 1 is a polynomial, just a constant polynomial. X is a polynomial. And now let's take a look at the graph. Right, let's graph 1 divided by x, graph, and you can see what it looks like. Okay, now, a couple things about that. One, I think the picture looks a little misleading. Does anybody know why I think it looks misleading? I mean, that's basically what it looks like, but not exactly.
They go like up and down indefinitely, but you can't tell that from the graph.
Yeah, it does go up and down forever. So really, this section should continue down. This section should continue up. This, I think it's easier to see, that does go left forever. That goes right forever. That's what the graph looks like. If you're doing this on an older calculator, what it might do, and I think I've shown you this before, is it might look like this. Oh, it actually didn't do it. Sometimes it connects it. Does anyone have an older calculator they use, or sometimes it connects it? I don't see anyone using an older one. Let me show you on this one. Let's see if it does it. Right, so I'm going to type in 1 divided by x and hit zoom 6. You know what? It might be hard to see what it's doing because the axis is there. So let me turn the axis off and see if it does what I'm thinking. No, it's not doing it. So sometimes on older calculators, it looks like it's connecting the graph. It should never be connected. I can't make it look connected. So that is how it's supposed to look. But I think on this one, it looks even worse in terms of, it definitely looks like it just stops. Those dots are a scatter plot. You can ignore those. But it definitely should not stop. Okay. So let's look at what happens as x approaches infinity and as x approaches negative infinity. What's happening to your y value? And it's the same answer for both. As x approaches infinity and as x approaches negative infinity, what's the y value getting closer and closer to? Yeah, Liam?
0.
Yeah, it's approaching 0. F of x or y is approaching 0. Will it ever reach 0? Okay, no. It's never going to reach 0 because pretend you plug in 1,000 for x. Your y value is going to be 1/1000th. If you plug in 1,000,000 for x, it's going to be 1 divided by 1,000,000. It's small, but it's not 0. It'll never be 0. What's the only way a fraction could be 0? Yep.
If you had a 0 on the top.
If you had a 0 on the top, and in this fraction, you will never have a 0 in the top. You're always going to have at least something. So no matter how much you divide it by, there's always going to be a little bit left. That's why it approaches 0. It never reaches it. Okay. And anytime you approach something but you never reach it, you have what's called an asymptote. Okay, so in our graph, y equals 0 is a horizontal asymptote for that function. Okay, and generally the way we show that is with a dotted line. Let me make that a little thinner. So what you would do is if you were graphing it by hand and you wanted to show the horizontal asymptote, you would put it in just like that. That's what the horizontal asymptote looks like. Now you might notice another asymptote in that picture too. We're not there yet. We'll talk about that one. But for now, we're just looking at the horizontal. So a lot of times people think an asymptote is a line that is never crossed, which isn't really true. You can cross an asymptote. Here's an example of a graph with an asymptote. And I'm going to draw something and it's going to cross it. Like this. The key with an asymptote is that as you start heading further and further away from the origin, it never crosses. If it crosses near the origin or early on, that's okay. But after a while, this graph is getting closer and closer and closer to it, and it will never cross again. That's really what an asymptote is. Some graphs cross the asymptote kind of early on. The kind of graph we're looking at here never does. Okay, so that is a graph where the asymptote is never, ever crossed. So any question on that? Yeah?
What would an equation look like where a line crosses the asymptote?
I think we're gonna look at one like that later this week. Off the top of my head, I can't remember the formula for it, but I know there definitely is one. I'll look it up. It's in the book after. So the idea is when you're thinking about a horizontal asymptote, you're looking at what's happening far away, as x approaches infinity or negative infinity. In fact, the picture that I just drew, they show that exact picture in the book. In fact, they even show one other case, which we don't really look at too much, but it's the idea that you're approaching a value even though you keep crossing it. It's like an oscillation, and that one I think I can show you. Sine of x over x. So if you look at this graph, and we set the window a lot smaller, let's try -1 to 1 and see if you can see it. All right, so what's happening here? Now, let me zoom out on the x scale a little more. Is you have a value that the graph is oscillating around. Okay, as you head further and further to the right or left, it's going to oscillate even closer and closer to it. Now I think you'll really see it. So it's kind of going up, down, up, down, up, down, up, down, up, and it's getting closer and closer. And they do consider that line an asymptote. We're not really going to be looking at one like that, but the idea is that it's approaching a value. Even though it keeps crossing it, it never stays at it. It kind of goes above it and below it and above it and below it, and it just keeps oscillating. So that's kind of an example of what I just mentioned, but it's a little different. But technically, that line is considered an asymptote because it keeps getting closer and closer and closer to it. Okay, any question on that? That's a little more complicated. We generally, again, don't look at ones like that. Okay. And page 217 has some more examples that I just showed you, including the one that oscillates. Okay, so let's find the horizontal asymptotes of that function. Okay, whenever you write a horizontal asymptote, I usually just abbreviate it HA, horizontal asymptote, and it's always y equals. Don't put x equals. X equals is something else we'll talk about. So, to find the horizontal asymptote, look at your expression, and basically let x get really, really big. Okay, so what happens to this fraction? As x gets bigger and bigger and bigger, what happens to the fraction 1 over x? It gets smaller and smaller, and it's approaching what number? 0. So as x gets bigger and bigger, that fraction gets smaller and smaller, basically approaching 0. So pretend you had 1 divided by a billion. So you've got 1 billionth plus 2. So what number is that very close to? A billionth plus 2. Yeah?
2.
2. This graph is getting very, very, very close to 2. And that's your horizontal asymptote. Will it ever reach 2? No, it'll never reach it. Because no matter how big you make x, this fraction is always going to be at least a very, very, very small number. It'll never be 0. Okay. How about this one? What's my horizontal asymptote here? Okay. It's -3. Again, if x gets really big, this fraction gets really small. So pretend that's a very, very small fraction, like 1/1000th. Okay, if you take 1/1000th and subtract 3, you're going to get like -2.9999999, something like that. Or if you take -1/1000th and subtract 3, you're going to get -3.000001. Right, so it's getting very close to -3. So any question on how to find a horizontal asymptote? All right, so now let's sketch that graph. Okay, so we already know what the graph of 1 over x looks like. Okay, that's right there. In fact, I can just kind of make a quick sketch of that right here. So that's basically the pattern we're looking at. What is this +2 going to do? Think about it as a transformation. Jay?
It's going to shift everything up 2.
Right, it's going to shift up 2. So, if just a quick sketch, not perfect, but if there's your lower part, and technically in this kind of graph, that's called a branch, because this is a hyperbola, but it's a hyperbola on a 45-degree angle. Usually when we sketch hyperbolas, you think of them as going this way, or that way. Well, this is a hyperbola on a 45-degree angle. So now, if you were sketching this with a +2, your asymptote would be normally right on the x-axis. Well, that's going to go up 2. The lower branch goes up 2. And the upper branch goes up 2. So all stuff we learned about transformation, shifting them up, down, left, right, everything still applies. So any question on sketching that, but thinking about it as a transformation, rather than just graphing it in a calculator and copying the picture? All right. Okay, so sometimes we can have a function that has two horizontal asymptotes. So we'll sketch this one and see what it looks like. And the way we're going to sketch it is we're going to break it into cases. And with each case, we will use long division. Or we could use synthetic depending on the problem. It's up to you. Okay, so I'm going to graph, and usually the first step to graphing something is to find the asymptotes. Because if you can find them, then it'll give you a good idea of what your graph is going to look like, because you know you should be drawing a line that gets very close to the asymptote. So let's find the asymptotes first, and then we'll make a sketch. Okay, we can use the calculator to help us with that a little bit. Okay, so that's what we're going to try to make a sketch of. Does anybody think they know what in that right-hand side of that equation is causing us to have to break this into cases? If this thing wasn't there, we wouldn't have to do it. Yeah?
Absolute value.
Right, it's the absolute value. So we're going to break it into two cases. If you're thinking about absolute value, what's one possibility that the result could be when you do an absolute value? There's really two possibilities. Either your number from the absolute value, either the number you plug into the absolute value is this, in which case you do something to get the absolute value, or your number is this, in which case you do something different to get the absolute value. Yep.
The number you plug in could be negative or positive.
Right, it could either be negative or positive. If it's positive, we don't do anything to it. So, or 0, we don't do anything to it either. So in the case where x is greater than or equal to 0, f of x just turns into that. Absolute value makes no difference if you're plugging in a number already greater than or equal to 0. So now we're going to work with this. Okay, but what we have to do is rewrite it so that it looks more like that. Okay. So, in order to rewrite it, let's do out that long division. So we've got, and we could do synthetic, but really it's not a very long division problem. Actually, technically it is a long division problem, but it's not going to be a very lengthy division problem. That was a lousy math. All right, so x plus 3 divided into x minus 2. How many times does x go into x? Once. Multiply it back out. X, 3. And then what do we do with the columns when we do long division? Yep.
Subtract.
Right, subtract them when you're doing long division. So x minus x cancels. Negative 2 minus 3 is negative 5. And I'm done. That's my remainder. So, the way I could rewrite this is think of it like this. Quotient plus remainder over divisor. Right? Just like you do long division back in grade school. So your quotient is 1 plus, or actually in this case it's going to be minus, my remainder over my divisor. And a lot of times, what they do is just switch the order on that. So they write it as negative 5 divided by x plus 3 plus 1 on the end. Either way, we can leave it like that. That's fine. Okay. So that's our first one. Okay, we'll come back to that. And now the second case is when x is less than 0. How do you take the absolute value of a number if what you plug in is less than 0? What do you basically do to the number? Yeah?
Just flip the sign.
And what's that called? Taking the what of the number? Not sure? Trevor?
Reciprocal.
Not reciprocal. That's when you flip a fraction. So he said the word flip, but it's really, well, I can't really tell you what I'm thinking without just giving you the answer. Yeah?
So take the negative of the number.
Yeah, take the negative, take the opposite of it. And the way she said it was actually perfect. Take the negative of it. So if that's your original problem, right there, and you plug in a number less than 0, that's basically going to turn into a negative x. Okay? Because by turning into a negative x, if x is negative, a negative negative becomes a positive. Okay? So now let's do the long division with that one. And I think what I'll do is I'm just going to circle this in red so it stands out. Okay, so we'll come back to that. And now let's do long division here. So negative x plus 3 divided into x minus 2. Okay, so I'm going to get negative 1, multiply back out. Subtract the columns. X minus x is gone. Negative 2 minus negative 3 is 1. Okay, so there's my quotient, there's my remainder. So negative 1 plus my remainder over my divisor. Okay, now we're going to focus on those two things. So let's look at the first one. If x gets bigger and bigger and bigger, what would be my horizontal asymptote in the first thing that I circled in red? Pretend you plug in like 1,000 for x. What I circled would get very close to what number? Sam?
6. No.
Well, let's plug in 1,000. What's 1,000 plus 3?
1,003.
And then what's 5 divided by 1,003? Well, roughly.
Like 200 or something?
No, 5. Like if you had $5 and you divide it between 1,000 and something people, what kind of number would that be? It would be. Can you be more specific about what kind of fraction?
No.
Anyone help her out? What kind of fraction would that be if you had to divide 5 between 1,000 something people? Yeah?
Well, it would be a really small decimal.
Very small decimal, right? 0.0 something maybe? So now if you have 1 minus a very, very small number, like say 0.001, what's that very close to? 1. Yeah. So the horizontal asymptote here for that one is y equals 1. And what about this one? Again, pretend x is 1,000. Negative 1,000 plus 3 is negative 997. 1 divided by negative 997, very small number. And you're adding that to negative 1. So what would you get very close to there? Megan?
Negative 1.
You get very, very close to negative 1. So those are your two horizontal asymptotes, at 1 and negative 1. And there's really no way to do that without just doing the long division. Okay, let's take a quick look at the graph. So we've got x minus 2. And I'm going to put that in parentheses. Divided by, I'm going to do parentheses again. absolute value of x plus 3. Okay, let's do zoom 6. And maybe I even want to set the x max and min bigger just to kind of see more what's happening. Let's go negative 30 to 30. And I think now it's pretty clear that as you head further and further to the right, your x value is approaching 1. As you head further and further to the left, it's approaching negative 1. And you can confirm that in the table. Like if you head really far to the right, like 50, you're at 0.9. Go all the way to 200, you're at 0.98 if you round it. At 2000, now you're at 0.998. Okay, but you're never going to reach 1. Eventually, if you type in a big enough number, the calculator is just going to round it to 1. But it's actually never 1. Same thing if you head the other way. At negative 1,000, you're getting very close to negative 1, but you never reach it. So there's your graph. And here's your two asymptotes. Okay, I like to make them a little thinner because I think if you make them that thick, it looks kind of confusing where it actually should be. So if you're drawing by hand, that shouldn't be a problem. But roughly like that. Okay, so it's kind of sandwiched between those two. Any question on that? All right. Okay, so we're going to go back to that same basic, the most basic rational function you can have. This time I don't want to look at what happens as x gets bigger and bigger. I want to look at what happens as x gets very close to 0. Because we know 0 is not a value in the domain. So as you start to get close to 0, something's going to happen to y. Can anyone tell from the picture, what does it look like is happening to y as you start to get very close to 0? Okay?
It starts increasing.
It starts increasing, yeah. And if you look at, like, let's do 0.5, y is at 2. If you go to 0.1, y is at 10. If you go to 0.01, now y just jumped up to 100. 0.0001, now y is at 10,000. So what's happening as x approaches 0 from the positive side, that's what that means, y is heading up to infinity. Now, let's also look at what happens as x approaches 0 from the other side. Let's come in from the negatives. When x is negative 1, we're at 1. Negative 0.1, we're at negative 10. Negative 0.01, negative 100. What's happening to the y value as I approach 0 from the negative side? What's y approaching? Negative infinity. It's dropping down. And anytime that that happens, where you have a value and it's approaching infinity on one side or negative infinity on the other, or sometimes both sides go to infinity, that can happen too. That's called a vertical asymptote. Okay, so vertical asymptote is as you get very close to it, all of a sudden your graph just takes off and goes to infinity or negative infinity. Okay, so in general, x equals some number is a vertical asymptote if as you approach that number from the left and the right, your graph either spikes to infinity or negative infinity. Could be both, like it was in this problem, or it could be both of them go towards infinity or both go towards negative infinity. Just depends on the graph. And the quick way to tell where your vertical asymptotes are as long as the numerator and denominator don't have any common factors. So as long as you don't have something like this. Let's say that was the top and that was the bottom. That wouldn't count. There's a common factor in the top and the bottom. But as long as there are no common factors in the top and the bottom, just like that, then your vertical asymptotes always occur where the zeros of the denominator are. It's basically the values that result in it being undefined. Now, does anybody remember what happens if the numerator and denominator do have a common factor? You don't get an asymptote, you get something else in the graph that's very small. And we talked about it when we talked about continuity.
A hole.
You get a hole. Okay, so be very careful. If the numerator and denominator have a common factor, you get a hole in the graph. You don't get an asymptote. So really, if you have to find the domain, that's also going to help you to find the asymptotes. Because the domain is all the values you can't use in the numerator. Well, all the values you can't use are the vertical asymptotes. Okay, so let's find the vertical asymptotes here. What value would cause me to divide by 0 there? Okay, 2. Shauna, what value would cause me to divide by 0 in example B? Not 3. 3 would be okay. That'd give me 6 in the bottom. What would cause me to divide by 0? Negative 3. And because it's a vertical asymptote, just make sure you write x equals. What if you write y equals? What would that be? That's a horizontal. That's different. This negative 1 has nothing to do with the vertical asymptote. It does have something to do with the horizontal. It shifted down 1. But the plus 3 shifted everything left 3. I'm going to skip the sketch on that. If I sketched it, it would basically just show you that this graph has been shifted right 2 units. So remember, you look at the number after the minus sign. If it's positive, it goes right. If it's negative, like this one, it would go left. That's a shift left 3, down 1. And that's the last one I had for that one. All right, so let's find the asymptotes here. And then I want you to list the transformations. What's the first thing you would have to do here to rewrite this so we can see it more like either example A or example B? And we did this earlier with the absolute value problem. How can I rewrite that? Yeah, let's do the long division. Now, if you said just find the vertical asymptotes, I would argue you don't need to do the long division. But if you want to find the horizontal, yeah, you do. You've got to do the long division out. So let's do it out because we're going to need it anyway. So that's going to give me 2. Multiply it back out. Subtract. Negative 13 plus 10 gives me negative 3. So, my quotient plus my remainder, in this case my remainder is negative, so it's minus, over my divisor. Now, looking at that box in black, I can easily tell, okay, I just want to make this clear, I can easily tell that that's what the horizontal and what the vertical asymptote is. What's the horizontal asymptote in that problem? Let's see.
2.
And how would you write it? Perfect. Y equals 2. Okay. How about, yeah, Megan, what's the vertical asymptote?
X equals 5.
X equals 5. Now I basically want you to describe the transformations. Okay, so describe how we can obtain our function from the one we have there. Okay. First of all, does anyone see how many transformations are happening? Yeah? There's more than 2. There are 3. If it's a little tricky, think of it like this. It's perfectly fine to think of it that way. Because when you multiply by a number in front, that does something to it. Okay? That's what's happening here. All right, so your transformations are, you would, let's start with our left and right shift. Okay, you guys have an order we're supposed to follow, and that's the first one here. So you're going to shift left 5 or right 5? What do you think, Gina?
Right.
Yep. So transformation 1, shift right 5. Now transformation 2 has to do with that 3. Does anybody remember what multiplying by a number in front does? Think about like if you had like x squared versus 3x squared. The 3 causes something to happen. It's not a shift left, right, or up or down. What else can you?
Would it increase or decrease the size?
In what way?
Never mind.
Yeah?
It would stretch it vertically.
Yes. It's a vertical stretch. So it does increase the size. We just have to be specific in what way. Vertical stretch by a factor of 3. And then the last thing is that 2, which a lot of times we see it written like, actually, 2 more things, and then we'll talk about the 2. A lot of times we see the 2 at the end. So we see it like negative 3 times 1 over x minus 5 plus 2. And when I started to think of it that way, then all of a sudden I saw the negative, and that reminded me of something else. What is the negative going to do? Remember what that negative does? Yeah?
Flip it over the y-axis.
Yeah, that causes a reflection. Okay, and that negative, that's with the vertical, so that would reflect it over
The x-axis.
yeah, that's going to reflect over the x-axis. Yeah, I'm just looking at your book, make sure that you do it in this order. The horizontal shift, the vertical stretch, the reflection, and then the last thing is a shift up 2. Alright, so the last problem we're going to do, we've kind of looked at these before. It's a mixture problem. Not as complicated as setting up a system though. So I'm going to give you the formula. I don't know if we'll have enough time to go through a whole example, but I'm at least going to give you the formula for doing it. First, I want you to understand that if you have a solution that they tell you is 50 ounces and 35% of that is acid in the solution, then if you multiply how much solution you have times 0.35, that tells you how much acid is in the solution. Maybe the rest of it is just water. Okay? That you need to know how to do. Okay, So this problem says we're going to add X ounces of pure acid. So we're going to take a 100% solution, pure acid, and we're going to add it to a solution we already have. Okay, the solution we already have is 50 ounces, and 35% of it at the moment is acid. I want to find a graph of the new concentration as I continue to add acid. Now, as I add more and more and more acid, what can the concentration approach, but it can never reach? Yeah? It can approach 100%, but you have to remember, you started with a solution that wasn't pure. So no matter how much pure acid you keep adding, it'll get stronger and stronger, but there's always going to be a little bit of the original left that wasn't pure acid. Okay, so the idea to find a concentration, you have to find the amount of acid and divide by the total amount. So how much acid did we start off with in the solution? We had 50 ounces of a 0.35% solution. So how much acid is that? Yeah?
17.5.
Yeah, you just use the same calculation we just did. So the amount of acid is 17.5, plus how much are we going to add? Yeah, we're adding X ounces. So that's how much acid will be in the solution. And the total amount, well, we started with 50, and we're adding X. If you graph that, it will give you a graph of the concentration. And it'll look something like this. You can start to add acid, and it's going to make the concentration higher and higher and higher, but it will never reach 1. Because 1 would be 100% as a decimal. Okay, so the last part I'll save for you, but the question is, how much acid do you have to add to make it a 75% strength? Well, if you just set our formula equal to 0.75 and then graph it on the calculator, you can find an intersect basically like this. Graph 0.75, graph what's in the box, and see how much acid you need to add. Okay, but we can take a look at that tomorrow. So the homework on 207, just a couple real quick graphs on the calculator, solving them. So it's 8 through 10. And then page 222, that's the stuff on rational functions. So it's 1 through 7 odd, 11 through 21 odd, 23, 25, 31, 33, 37, 38, and on 48, I only want you to do parts A and B. I think 48 has a part C. You can skip that.